Much. So let me begin with expressing my thanks to organizers, especially to Indranil, for inviting me here, the opportunity to talk. And I would like to stress that this paper is also, as say, many results here are inspired by my joint work with Indranil, but somehow we will see how it is related a bit, maybe slightly to the main topic of this conference. So, and following also Georg, I will also say a few words about University of Warmia and Mazury. So, this is a relatively big regional university in northern Poland. It's a university of the province, which is called Warmia and Mazury. There live Warmians and Mazurians. They don't like when you mix them up. So there are two basic types of inhabitants, Warmians and Mazurians. So that's the university is relatively big. It's 40,000 students, and it has very eclectic curriculum, ranging from animal breeding to medical sciences to mathematics. So how it looks like. So okay. So and I want to say that it's a joint work with Vicente Munoz and Juan Angel Rojo. Oh, sorry, not this. So okay. So maybe again the title. So Homology SmaleBarden manifolds with K-contact and Sasakian structure. So what I will do, I will explain both definitions of K-contact and Sasakian structures. Unfortunately, they are a bit lengthy, but then I try to explain how we can view this as manifolds, which are in fact orbifolds, and so we can forget about these geometric structures and work in a bit different way. But nevertheless, I will start with a formal definition. So, and I simply, just to fix notation, I want to fix my notation for symplectic and Kaehler manifolds, because both will be the main building blocks. So, symplectic manifolds, we fix symplectic for omega. I will always assume that all my manifolds are compact and say closed, so without boundary. So we have, as usual, we have a compatible Riemannian metric and a compatible almost complex structure. So here is our, say, formulas for this. So J is a compatible almost complex structure, so it is preserved by omega, and if we define the symmetric form G by the formula omega of Jxy, then we get a Riemannian metric on M. This is a compatibility. And of course, in this notation, my Kaehler manifolds are simply triples G omega J with J integrable. So it means that the Neuenhuis tensor vanishes. So and then we have Kaehler manifold. So contact manifold. Then we have to fix. I would say that I consider it a slightly less general situation. Normally such manifolds are called co-orientable contact manifolds, because I fix contact form. Basically fix only distribution, but I fix contact form. So I have a closed odd dimensional manifold M to n plus 1. I have a contact form eta. It's a one form, which is say, non-degenerate in maximum degree, as much non-degenerate as we can. So it means that d eta to the nth power times theta is not zero everywhere. And then with this contact structure, this contact form, one associates two objects. The kernel of this form, this is a distribution of codimension 1, simply a kernel. And then these formulas below, theta of psi equals 1 and I psi of d eta equals 0, they determine Reb vector field. So with each contact form, we associate a distribution F and a Reb vector field psi. I will always write psi for Reb vector field. And then finally, we have a formal definition for K-contact manifold. So the definition of a K-contact manifold is a kind of making everything Riemannian. So we take the contact form, but also want this contact form to be, in a sense, compatible with the Riemannian metric. We want to go somehow to a framework of Riemannian geometry. And then a formal definition is as follows. The M eta is K-contact if there is an endomorphism phi of the tangent bundle such that the square is not minus identity, because we have extra dimension, but instead we have that the 1-1 tensor psi tensor to eta, yes, so this is an extra correcting term to this phi square, and then the compatibility of theta with phi means this formula that d eta phi x phi y equals d eta x y. This is our demand of compatibility theta with phi. And we also demand that what we get should be a Riemannian metric. So d eta of phi x is everywhere positive on the kernel. Not everywhere, but on the kernel. And the Riemannian metric is determined by this, defined by this formula. This formula should define a Riemannian metric. It's a part of the definition. And finally, the final demand is that psi, remember that psi is a Reb vector field, but this Reb vector field should be killing. So the Lie derivative along psi of the metric should be 0. This is a killing vector field. Here is our definition, maybe lengthy and maybe, but you will see that it goes. And finally, we have our final object is Sasakian manifold. So contact manifold is an odd-dimensional counterpart to symplectic manifold. And then we want to have something which is odd-dimensional Kaehler manifold. Yes, something which is an odd-dimensional counterpart. So for us is the following. So recall that, again, that we have all these objects which constitute K-contact manifold. So it is a manifold, a contact form, and an endomorphism phi, a Riemannian metric G, and Reb vector field which is killing, which we call psi. So now we have these 5 tuples. So M theta phi psi G, which is a K-contact manifold. And we define an extra object, which is called metric cone. So it is really it's a cone. And on this cone, you have, say, something like word product metric. Yes, so it's not product metric, but a metric defined by this. You take the T, it's of course, it's a coordinate on real line. So it's a coordinate on real line. So you have d theta squared, it's a metric on the real line. And so you have the same T square as a coefficient with G. And then you get the Riemannian metric. And so we define I as follows. It's endomorphism of the tangent bundle to this cone. And we simply define it as a formula which immediately shows you that it is a almost contact structure, yes? Because I of x is phi of x, and phi square was identity on the kernel. So it's minus identity on square equals minus identity on the kernel, and on the rest is t, d over dt, and psi. There are 2 vector fields more. Then I of psi is t d over dt, and I of t over dt is minus psi. So it's clear then from the definition that I is an almost complex structure, and our definition is that if it is integrable, then it's Sasaki. So it's somehow not clear for the moment that it's the right understanding of what should be an analog of Kaehler, but it is. So it's our odd-dimensional Kaehler manifold. So of course, the best way to try to understand what object we are dealing with, we would like to have some prototype, some prototype example. So the prototype example will be a so-called Boothby-Wang vibration. So how we can look at Boothby-Wang vibration. So take any symplectic, compact symplectic manifold, B, omega B. Assume that omega is integral. This is the second homology with Z, with integer coefficient. Take the corresponding circle bundle. And there is something which I won't give a proof of this. Yes, it's a classical result of Kobayashi's from the 60s, that on such a circle bundle, there exists a special connection. So it's a connection form theta with the following property, which is written here, that d theta equals the pullback of the symplectic form. This, I won't give you the proof of this because it's, I thought a bit when I tried to prepare this talk. The proof is, of Kobayashi is really solving differential equations, locally solving differential equations. And then it's lengthy. But somehow he showed by local calculations that this connection exists. Because it exists, you can see that you can at least somehow believe that it will give us a K-contact structure. Why? You see that theta has the following property. Remember that it's a circle bundle, so the fibers are one-dimensional. So you pull back symplectic form. So on the horizontal distribution, your d eta is a symplectic form. It's a symplectic form. So if you now multiply it by theta, you will get a contact form. So it's a contact form. Because it's a contact form, and it is a connection form, so it's circle invariant. Because it's circle invariant, some say, thinking over will tell you that these compatibility conditions are satisfied. Although it requires some work, but nevertheless, it's an explanation that because of the formula d theta equals pi star omega b, you have a connection, then you have a horizontal distribution, you have a symplectic form d eta on the horizontal distribution. So theta times d theta to square is nowhere zero, so it's a contact form, it's circle invariant, and then you can define a Riemannian metric. Why? You can take the so-called connection metric. So a metric which is also a pull back from the base on the horizontal distribution, and you take the fiber, take the Riemannian metric on the fiber, and declare this to orthogonal, and then you get a Riemannian metric, and this is compact. So our prototype is as follows: that any Boothby-Wang S1 bundle carries a K-contact structure. If B is Kaehler, then it is Sasaki. So then, of course, the simplest example which we can get, it's a Hopf bundle. Hopf bundle is Sasakian. So, of course, you can find explicit formula for Sasakian structure on the sphere, but nevertheless, using this, you can see that Hopf bundle is the first and the simplest example of this situation. And then, now we will see that it's our basic construction. There is only some, maybe not trivial, but modification of this. So what is the general case? The general case is as follows, that if we have any K-contact manifold, we know that our Reeb vector field psi is killing. And because it is killing, it defines, in fact, a circle action. And, or we can say that it defines a Riemannian foliation. And because it's Riemannian foliation, then in reality we get a theorem, which I will now try to formulate. So, and we have for the moment to consider a bit specific class of K-contact structures, which are called quasi-regular. So this K-contact structure M theta psi phi g is called quasi-regular if there is some positive integer such that for any point in M there is some neighborhood such that each leaf of this Riemannian foliation passes this, neighborhood, at most Q times. Then what we get is so-called Seifert fiber bundle. So in the simplest situation, we have a Boothby-Wang fibration. These are true circle bundles. These are true circle bundles. But if we consider quasi-regular, then we have the following theorem. If we have a quasi-regular K-contact structures, then the orbit space has a natural structure with symplectic cyclic orbifold. And the projection is a Seifert bundle. And if M theta psi phi j is Sasakian, then this orbit space is a cyclic Kaehler orbit. And in fact, from this moment, we can forget about these tensors. And in fact, what we are interested in is this type of construction. So we have a Seifert fiber bundle, and they are defined over cyclic, symplectic, or Kaehler orbifolds. And then finally, yes, it's principal bundle. Then it's co-equals 1, it's principal bundle. So now to be able to consider only this situation, we can simply, we can simply quote a theorem of Rukembira, which I also won't explain. The theorem of Rukembira is that any K-contact manifold admits a quasi-regular contact structure. So if you have any, you can slightly modify it and get a quasi-regular one. And if you have Sasakian manifold and Sasakian structure, you can slightly modify it and get a quasi-regular. You cannot get regular this way, but you can get quasi-regular. And then, because of that, we can always consider, in the questions which are interested in, we can always consider quasi-regular K-contact structures. So then I will maybe try to say a bit about what understanding of these orbifolds we need. Georg already explained a lot about orbifolds. I need a bit more specific situation. I need only 4-dimensional case, and I need cyclic orbifolds. So when there are cyclic orbifolds, then we have orbifolds which are oriented. So our isotropic groups are in SO4. And we consider cyclic orbifolds, so all our groups, isotropic alpha, these are cyclic groups. And then locally, I need local description. So locally, we have something like that, if we have a chart, then we can center it at 0, and then because gamma is some Zm, we can conjugate this gamma with a diagonal matrix acting on C2. And so we always can consider our local charts, this U tilde as C2, gamma as a cyclic group with generator written here as exponent of 2 pi I divided by M, it's of order M. And then the action, local action is given by this formula. And then we will say that M is an order of a point, X in X, and we set the M1 and M2 as a greatest common denominator of G1 and M and G2 M. So these numbers, M1 and M2, are called multiplicities of this corresponding isotropy surfaces. So this is a local description. And we need it. So we need maybe some terminology. So our understanding of local classification points in our 4-dimensional cyclic orbifold. So these are regular points. It means that this order is 1. So they are simply regular points. But if M is greater than 1, it means that it's isotropy point. Then there is an isotropy. But then we have something which we need, it's called smooth points. So smooth points are also isotropic because still we demand that m of x is greater than 1, but we want this chart U be still diffeomorphic to a ball. Then it is a smooth point. And singular points, these are points which are not smooth. And then in the, in the sequel, we will always use extra assumptions of semi-regularity. I don't know if it is, if it is our terminology or is somebody else who used it. So we consider orbifolds whose all points are smooth. We consider only orbifolds with smooth all points, but with isotrope. So example how we get smooth points. Yes, so if m equals to m1 times m2, Zm is psi, m1 is greater than 1, m2 is greater than 1, but the greatest common denominator of G1, G2, and J1, J2, m is 1. So locally we have two isotropic surfaces, yes, Z1, 0, 0, Z2. These are isotropic surfaces which intersect transversely in one point. And the multiplicity of D1, you can see, is M2. The multiplicity of D2 is M1. And Zm acts on C2 as follows, as Zm2 times Zm1. And then, of course, it means that it is diffeomorphic to the ball. So, and this is our general picture. We need this intersection in two points. Oh, sorry, two surfaces in 1 point. Okay. And then, finally, construction determining orbit invariance. So this is a proposition which we in fact all the time use. Let X be a symplectic smooth-oriented Four manifold with symplectic surfaces di intersecting transversely and positively, and coefficients mi greater than 1 such that they are relatively prime. And this, if relatively prime, if di and dj intersect. If they don't intersect, then Then there exists a smooth symplectic orbifold X with isotropy surfaces di of multiplicities mi. So it's our, in fact, in a sense, it's our basic construction. X is, you take a symplectic smooth manifold X, gives this structure, and give this structure. So this is a thing that, for example, for me, when I started working on the problem, I had very poor knowledge of orbifold, so it took me a very long time to understand that I have this smooth, and then change the structure in a way to get orbifold structure. So, and then even but I will skip it. I will simply say that, here is the way how you do this. So you explicitly put a new atlas, which is an orbifold atlas on your four-dimensional symplectic manifold. So you need fix some Riemannian metric, you need some balls, you take that if it is away from dA, dj, then we take a smooth chart. If not, we have to modify it and define explicitly a circle action, Zm action, and then check that everything works and goes through. But you can do this. And finally, Seifert bundle. So if you have this smooth orbifold, then you can construct Seifert bundle over it. So here it's the formal definition of the Seifert bundle. It's an orated 5 manifold equipped with a smooth S1 action and a continuous map such that for each orbifold chart there is a commutative diagram. So it's a usual, orbifold definition of a bundle. So you glue orbi-bundle by this construction. And then Seifert bundles also have orbifold invariants. You see here we have orbifold invariants, this di and mi. These are surfaces, symplectic surfaces, and their multiplicity. So basically, if we have a orbifold, symplectic orbifold, what we need a symplectic manifold, and we need a pattern of symplectic surfaces with prescribed mi. These are our data. And for orbi-bundle, we have more, for Seifert bundle, we have the same. Our description of the Seifert bundle is given by the base, which is a smooth orbifold with invariants di, mi. And then to get the Seifert bundle, we need the analog of the first Chern class. And then we have this orbit invariance of Seifert bundle. So to get Seifert bundle, we need di, mi, ji, and Chern plus. And the Chern plus determined by this formula. I will only mention what is Chern plus in this particular situation. We simply argue as follows, that if you have a Seifert bundle and Zm, then S1, if Zm is S1, then S1 divided by Zm is again S1. So it's, if we divide by the action of this group, we again get a Seifert bundle. So if we have mu as a local common multiply of all mx, this isotropy orders of m, then if we divide by Zm, we get a manifold. And then we know what does mean Chern plus. So this is our definition of the Chern plus of the Seifert bundle. So finally, when we speak about Seifert bundles, we simply keep in mind that we have the following data. X, smooth manifold, a pattern of symplectic submanifolds, the di, numbers, prescribed numbers, mi, ji, and the Chern plus. Yes, yes, yes. No, yes, now, yes, now it is, yes, yes, it is, yeah, now it is. So we have this second. So we get the same situation and in the principal bundles. If you have C1, you have a corresponding circle action on a 5 manifold. On a 5 manifold. So this is. So let me make a conclusion to the first part. So the conclusion is that if we have K-contact or Sasakian manifold, then our point of view is as follows. We simply have a Seifert bundles over smooth cyclic orbifolds with symplectic or Kaehler structures. And our data are a smooth symplectic or Kaehler manifold, orbit invariants, di, mi, ji, and the Chern plus. First Chern plus. This is our data. So we somehow, I think about my problem, which I will formulate. I think in this data. These are my data, which define all my structures and define all this K-contact, etc., etc. All these are my data. And so now I finally, after half of an hour, I will go to formulate problems which are interested in. So more or less in the book which was published in 2009, Boyer and Galicki formulated a kind of research program. And this program is as follows. It's already known that there are topological abstractions to the existence of K-contact or Sasakian structures on compact manifold of dimension 2n plus 1. So Sasakian manifolds have the property that they have even Betti numbers for p odd with this restriction on p, on pi, on p. So this is evenness of the p Betti numbers. There are some torsion abstractions in dimension 5 discovered by Kohler. I will talk about that. The fundamental groups of Sasakian manifolds are special. The cohomology algebra of a Sasakian manifold satisfies a version of the hard-left. And there are some so-called formality properties of the rational homotopy. So they formulated the program, study topological properties of K-contact and Sasakian manifolds, and in particular, understand the question of K-contact versus Sasakian. So some people remember, some not. In the 90s of the previous century, there was a huge activity, symplectic versus Kaehler. How to construct symplectic manifolds which do not carry Kaehler structures. Basically, they distinguish between Kaehler and symplectic structure using various homotopic invariants. For example, evenness of the Betti numbers, or maybe formality, or what else. So, and then at some point, people asked the same question for odd dimensional counterpart. So even dimensional case is somehow Kaehler versus symplectic, and odd dimensional counterpart is Sasakian versus K-contact. So then it's this question. And then they explicitly, they formulated the problem. Do there exist simply connected, closed K-contact manifolds which do not carry Sasakian structure? So do there exist simply connected, closed K-contact manifolds which do not carry Sasakian structure? Well, why simply connected? In the non-simply connected case, the problem is much easier to solve, and it was solved. Because of that, the more difficult part remained, it was simply connected. So in our paper, which recently appeared within Daniel, Fernandez, Munoz, and myself, well, it's a paper about a bit, it's paper more broad topic, but from this paper you can derive the positive answer in dimensions greater than 17. But because it's simply a corollary to some work here. Then myself and my colleague Haidu and independently Capelletti Montano answered positively in dimension up to 9. Recently, in 2015, we published with Vicente Munoz, we published a paper which settles dimension 7. All this, why all this I put separately? Separately, because all this, to prove all this, you can use homotopy theory. There is nothing more. So you can do homotopy theory and comparing topological invariants, you can distinguish Kaehler, Sasakian, and K-contact. But in dimension 5, the problem is challenging because you cannot do any homotopy theory anymore. The dimension is too small. And then you have to do something else. And then we worked hard for some time to invent some idea what to do with 5-dimensional case. So the question is, do there exist Smale-Barden manifolds which carry K-contact but do not carry Sasakian structure? Smale-Barden means one connected, closed, 5-dimensional manifold. Why they are called Smale-Barden? Because it's a kind of exception in the whole mathematical world. If you have dimension 4, then you know that there is no reasonable classification of 4-dimensional closed manifolds, smooth closed manifolds. In dimension 6 and so on. But in dimension 5, there is full classification of this manifold. They are classified by the torsion in the second homology group and by Stiefel-Whitney class. So they are absolutely classified. And so people, of course, were very interested. Can you put K-contact structure in when, and can you put Sasakian structure? And can you distinguish this or not? So this was a bit challenging. Dimension 5. So, and then you see that really we do not use homotopy theory anymore, and what we do instead. So dimension 5. Well, I will recall because we already discussed this, but I simply recall how we view our K-contact and Sasakian manifolds. We view them as Seifert bundles. So X omega is symplectic Orbifold, and M over X is a Seifert bundle with Chern class, which is the cohomology class of the symplectic form. Then M admits a quasi-regular K-contact structure. We know this. And if X omega is Kaehler, then this structure is Sasakian. How to prove this? Well, the proof is Orbifold version of a theorem which I showed you for manifolds, for bundles. Then it is the proof. And then we know, it's the only idea which we had. Then we know Kaehler-Bailey theorem, that the Hodge Orbifold is a projective algebraic variety. How could we try to use this? And what is the difficulty with this? So what would be possible strategy? Strategy, because we believe that still there exists such manifolds. So, because we believe that there exist K-contact 5-dimensional Smale-Barden manifolds which are not Sasakian. We try to prove it. So what would be the construction? Well, first, of course, it is easy now to find symplectic manifolds or orbifold, which is not Kaehler. This we know how to do. So we can imagine something like that. We will take closed symplectic, simply connected manifold and build a Seifert bundle over it. Then we know that it is K-contact. But it doesn't mean that it is not Sasakian. Why? Because there is no any guarantee that there are no other Seifert fibrine over projective algebraic variety. The same manifold M may be fibered in different ways, and so it might happen that that we started with X, which is symplectic non-Kaehler, but it will fiber in another way, and we will get Kaehler, and then it gives nothing. So we don't know. But we try to somehow to continue this line of reasoning. And unfortunately, we had to restrict ourselves and to weaken our hypothesis. And we still cannot prove the theorem in full generality. But what we think is that we understand the problem. We understand. So what is our understanding? So we restrict a bit to our orbifold. So an orbifold X is semi-regular if all points of X are smooth. I told it already. And we say that 5-manifold is Homology SmaleBarden if H1 is. So we cannot prove that it is simply connected, but we assume that we will consider the case where H1 is the first step. It's the first step in our attack. So Homology SmaleBarden, it means H1 equals 0. And then we prove the theorem. And the theorem is proved. There exists a Homology SmaleBarden manifold which admits K-contact structures and does not admit any semi-regular Sasakian structure. So we consider that these semi-regular assumptions that all points are smooth, we consider it as purely technical and simply didn't want to go into too many technical details. But what about Homology SmaleBarden? It seems difficult. And I will tell why it seems difficult. So well, but it's a first step in the say solution, and it seems that we reveal some kind of. And now I will tell you the scheme of the proof. And unfortunately, I will formulate the theorem exactly, and so I will make this formulation several times to somehow to make all this visible. What is the proof? So the first theorem which we prove, it's as follows. There exists, it's an existence theorem. There exists a simply connected symplectic 4-manifold with the following property. B2 is 36. There are 36 generators in the second homology. But what is important, all these homology classes are generated by symplectic surfaces. So there exists 36 disjoint symplectic surfaces, S1, S36, such that their homology classes generate H2. And, well, what is written here is simply the genera. So it's, although it's written in this way, but it's simply genera. We calculated the genera. And the genera of these symplectic surfaces are, there are 27 surfaces, which genus 1, so there's a tori. Then there are 3 symplectic surfaces with genus 3. These are pretzels of this type. There are 3 surfaces with genus 2, and also, again, 3 surfaces with genus 1. But what is important, we calculate the intersection numbers, and the intersection numbers are as follows. It doesn't matter for the moment which they are, but important is that because of this, we know that this is the proof that they generate the homology, because the intersection matrix is the right intersection matrix. So this is the first theorem, yes? That there is a 4-dimensional, simply connected, symplectic 4-manifold with B236 and all homology classes generated by symplectic surfaces. And then proposition 1. Now you should keep in mind this theorem on construction of Seifert bundles. Your Seifert bundle is simply a manifold and a pattern of symplectic surfaces with multiplicities. So now the proposition 1 is as follows. Take a prime P and choose numbers Gi as genera in the previous theorem. There exists a five-dimensional K-contact manifold with H1 equals 0 and with H2 of this type. There are Z35 and torsion elements in the second homology of this type. There are 36 torsion generators expressed by this formula. So for a moment, believe that this theorem is true, that such five-dimensional contact manifold does exist. It exists because of the things that I told you before. Simply, you take the Seifert bundle over this manifold. Okay. And then proposition 2. It's a same kind of converse. Suppose that M is a 5 manifold with H1 equals 0 and H2 given by the same formula, Zk. These are non-torsion elements, and the torsion elements of which number is k plus 1, and this elements, they are torsion elements with p prime, and gy greater or equal to 1. If M over X is a semi-regular Seifert bundle, then necessarily the homology will be as it should be. So H1 equals 0 and H2 equals to Zk plus 1. So this semi-regular Seifert bundle kills us this torsion, and we get, but it gives us a new generator. And moreover, the ramification locus of X is k plus 1 disjoint surfaces di, linearly independent in rational homology, and of genus, and there are of right genus, Gi. And finally, proposition 3, under the assumptions of proposition 2, if X is a smooth Kaehler Orbifold, then X is a smooth complex manifold, and Di are complex curves intersecting transversely. And finally, the following theorem. Let S be a smooth Kaehler surface, now Kaehler surface, with H1 as Z, and containing B equals B2 smooth disjoint complex curves with the G of the same G, yes, the same G general, and spanning H2 as Z. Assume that at least 2 Gi are greater than 1. G is maximum of Gi is less or equal to 3. Then we have an upper bound for B, for B2. For the second Betti number. So let us now go back and we'll see what happens. So I will maybe explain once more, but you see, this is your symplectic manifold. It has B236. And then take your Seifert bundle over it. You have K-contact manifold. And then because of all this proposition 1 and proposition 2, you know the homology. You know the homology. And then by proposition 3, you know that if something will be fibered over Kaehler as a Seifert bundle, then they should be complex surfaces, complex curve intersecting transversally and exactly with the same homology and with the same Betti numbers. But then it's a contradiction, because if you assume that there is a Kaehler structure, so Sasakian structure, then you should fiber it in some other way, but still with this data. But why still with this data? Because proposition 1 and proposition 2 do not depend on any structure. They depend only on several actions. So finally, you cannot fiber in any other way, and that's the reason. So what are now difficulties? Well, the difficult part of all this is, of course, this. Maybe I will even make some summary of this. So main steps of understanding. What we use. Difficult part, but not for us, but for Kaehler, it was calculating this homology. In fact, what we did, we read very attentively a paper of Kaehler and derived from this paper properties of homology, and noticed that they don't depend on which structure you put. And then this is a very important paper of coherent topology. It gives you homological information. And then there is a difficult, for me, for Vicente not, because Vicente can do all this very well, and I not. So for me, it was very difficult part. It's the algebraic geometry part. So here, all people can somehow imagine how this proof goes. So we simply have our data. We know that it is algebraic for so it's a complex algebraic variety. So we have much more invariants than in symplectic world. Yes, we have irregularity, Netter formula, Riemann-Hodge relation, etc., etc. And so manipulating with line bundles determined by this divisor di, well, we have a lot of constraints, and using some very elementary, say, identities, various types, whereas combinatoric argument essentially due to Vicente, which shows that B2 should be less than 2G plus 3. But then we knew that our basic problem is how to construct a simply connected symplectic form manifold X with a pattern of symplectic surfaces, generating the second homology, intersecting transversely, and with the same genera, but violating this restriction. And we found this B2 equals 36. Yes. So it was crucial. Finding this example of such a symplectic manifold was crucial. The rest was done by algebraic geometry, which is, if you know this, you can read it as it's standard. This was difficult, and of course, understanding Kaehler's work and noticing that homology does not depend on this. And then simply we take, so defining an orbifold structure next with smooth points by declaring Si to constitute a ramification locus. This will be our isotropy surfaces. We demand multiplicities, take Seifert bundle with this Chern class, and that's all. And it's our manifold. What we need, finally, this is the last part of my talk. This is the part which I understand better. So this is a construction of X. So how to construct simply connected four-dimensional symplectic manifold with 36 symplectic surfaces with genera less or equal to 3. At least 2 have G of Si greater than 1, and such that Si generate second homology. Well, what to do? Well, only try to do symplectic surgery of building blobs which are visible. So we need some building blocks, and we will do symplectic surgery, and of course we need our surfaces to say that we have something which is some homology class realized by surface. We at least need to see it. Yes, so we need some building blocks where we see symplectic surfaces. So what constructions to use? Well, symplectic resolution of transverse intersections, symplectic blow-up, Gompf symplectic sum. So, and what building blocks may be? Tori, in tori we see tori, yes. Elliptic fibrations. In elliptic fibrations we see fibers, and they are tori, yes. And it was somehow I don't know anything else to do. So, and I simply remind you quickly Gompf symplectic sum, how it works. So we take two symplectic four-dimensional manifolds. We have two symplectic surfaces embedded there with normal bundles with opposite orientations and with the same genus to have symplectomorphism. So fixed symplectomorphism and orientation reversing orientation preserving diffeomorphism. So isomorphism of the normal bundles, and then we take this diffeomorphism of a disk, which turns this punctured disk, which turns it inside out. And then identify these normal bundles with removed submanifolds, and then glue according to this map phi. This, what we get is a Gompf symplectic sum, a Gompf proof that it is really symplectic. So it's a usual surgery, but in a way that it is in codimension 2, and then a Gompf proof that you can put symplectic structure on this. Symplectic blow up, I will simply recall notation because I need one thing. I need exceptional sphere there. So, so if we have a symplectic manifold, take a Darboux ball, put standard complex structure on this, then you see this d tilde, and then you see the sphere in this d tilde, and then you blow up as this gluing. Then you see the sphere there. And so topologically, it's known that it is simply a connected sum of X with the CP2 with reverse orientation. And you see this exceptional sphere here, this E. And you know that it is known that the self-intersection of E is -1. It is so-called exceptional sphere. So if you have a blow up, you can have exceptional sphere there of self-intersection -1. And finally, elliptic fibration. So elliptic fibration, I have only one. I need only one. It's CP2 blown up in 9 points. So then you take two generic cubics, intersect. You know that two generic cubics intersect in 9 points, so you remove these 9 points, and then there is only one cubic going through any point Q. So you have a natural map, which after blow up can be extended to this CP2 blown up in 9 points, and the generic fiber is a torus. So we see these surfaces. So a generic fiber in this elliptic surface, a torus in a torus, and an exceptional sphere in blow up. And then finally, one more proposition which you, in fact, somehow could imagine. So if we have two symplectic surfaces which intersect transversely, and positive symplectic surfaces N1 and N2, and if we glue our symplectic manifolds and do Gomp symplectic sum along this N1 and N2, so do this Gomp symplectic sum, and then the surfaces which intersect transversally will also glue together. And there, this you can see. Maybe you cannot see, but it is calculable that then the self-intersection will be C1 square plus S1 square plus S2 square, and the genus will be given by this formula. And there is also a known fact which we use, that every exceptional sphere in the blow up is a section of the elliptic fibration. So our exceptional spheres are sections. They intersect generic fiber in 1 point. And so final construction, which is here. You take a configuration of 6-story ET4, this type. You take a symplectic form. Well, we take this form to make all this symplectic. So because we need some small perturbations of all this. So this symplectic form is maybe not canonical. And you do the following symplectic sum. You take your tori. This configuration is as follows: T12 intersect transversally with T34. T23 is intersect transversally with T14. T13 intersects with T24. And then you take your elliptic fibration E1 and take generic fibers. And it's a misprint here. So you glue the torus T4 to T12. You glue together with a generic fiber F2 of the first copy of the elliptic fibration. Then you take T13 and glue with generic fiber of the second elliptic fibration. And then you take T14 and glue with the last elliptic fibration. So you glue 3 elliptic fibrations along generic fibers to your configuration of tori. And you get then, and finally it's not the whole thing, you get some manifold Z, and then you blow up Z into points. And then what you get, it's exactly the manifold you need. And so, of course, well, this requires some work. Because of that, I won't give you all details and all surfaces, but I will show you surfaces which you can easily see. So what surfaces you can easily see? Take elliptic vibration, then it's, as you already saw before, there are 9 sections. So 9 exceptional spheres. There are 9 exceptional spheres, but they intersect a generic fiber in one point. But then what does it mean? It means that E1 intersects F2 and it transversely. But T1,2 intersects T3,4 transversely. So if we glue this together, then E1 will, this exceptional sphere, we will glue to T3,4. So you get a sphere and you glue torus. You get a torus again. So, and it is still a torus, and self-intersecting will be still 1, minus 1. And then you can, you have S1, S9. First 9 surfaces, it's the first copy. S11, S19, it's the second copy. And S21, S229 is the third copy. And so you have already 27 surfaces. Then what 3 surfaces you also can see, it's because if you take a generic line in the elliptic vibration, then you know that it intersects the generic fiber in exactly 3 points. Then you again do the same, and you get 3 more surfaces. Yes, and then so it's finally totally, we have 30 surfaces, and we have 6 more. Unfortunately, it is technically more complicated. You need elliptic vibrations, vanishing cycles, and various things, Lagrangian cylinders. It's a lot of work. But finally, these 6 surfaces are obtained, and the only thing that which I want to complete my talk, is that you see that X is 1 connected, X is 1 connected by Van Kampen, which we glue it that we know that it is connected by Van Kampen, but we don't know how to calculate pi 1 in the case of Seifert bundle. Simply we don't know how to do it, and the only thing that recently Indra Neil showed me something that may be helpful. But you see that, well, philosophically, Higgs bundles might be somehow useful in a sense when you want to understand pi 1 of any manifold with geometric structure. Yes, so you could try to think over it. Yes, so this we simply don't know what to do, and it's all. So the first step is done. The other might be much more difficult. So there are some references. This was paper which was somehow inspiring from the very beginning. Then this, and simply I wanted to somehow recall my old book from 1997, which summarized all this business with symplectic versus Kaehler. And this is very important paper of Kaehler cycle actions on simply connected 5 manifolds in topology. So these are main things to help us to do this work. And finally, I wanted 2 quotations about Sasakian geometry. So Bourguignon said, several dominant figures of the mathematical scene of the 20th century have step after step along a 50-year period transformed the subject, so Kaehler geometry, into a major area of mathematics that has influenced the evolution of the discipline much further than could have possibly been anticipated by anyone. And Krzysztof Galicki, Sasaki seemed to have had both the necessary intuition and a broad vision in understanding what is and what is not of true importance. So it's about Sasakian geometry. And finally, I wanted to learn who was Sasaki. And unfortunately, learned very little. So because somehow he was very somehow cautious not to make public his private life, so nobody knows. But anyway, he was born in Yamagata Prefecture in 1912 in a farmer's family, brought up by his uncle who was a superior in a Buddhist temple, studied in Tohoku Imperial University. Since 1935, worked in differential geometry under the guidance of Professor Kubota. Got PhD in 1943. In 1946, appointed to the vacant chair after Kubota's retirement. In 1960, introduced the notion of normal metric contact structure, which is equivalent to Sasakian structure. Major works were written in 1962-67, but all notes were in Japanese. He created, in fact, a subfield of Riemannian geometry, professorship in Tohoku University until 1976, visited in Princeton, worked with Veblen, Morse, and Chern. His biography is not well known, Even his obituary appeared only in a local newspaper. Thank you very much.